We're recording. All right, so types of reactions, you guys. Back in Honors Chem, you learned that there were 5 types of reactions, but of course now we know that there's many more types, including like acid-base reactions and redox reactions. But let's start with a review of our 5 types. And I'm just gonna go straight to an example. A synthesis reaction, you know a synthesis reaction is happening when you've got 2 or more substances coming together to form just one thing. So you know it's synthesis when there's only one product. Ooh, handwriting's not warmed up yet. Okay, so one product. Let's do an example of a synthesis. Oh, here's John. Good morning, John. Okay, so synthesis. Let's do synthesis of magnesium oxide. So if we've got some magnesium solid reacting with oxygen in the air, I'm going to leave spaces for balancing here. Don't forget your diatomic elements, oxygen gas being one of them. When we form ionic compounds, of course, we have to balance our charges. And so the formula for magnesium oxide is MgO. Think about your solubility rules. Do I even need to consider a solubility here? I do not need to consider solubility here because there's no water present. So I know if I'm forming an ionic compound and there's no water present, the state of matter for my ionic compound is definitely going to be a solid. Can you guys just make sure you guys are muted? Because I'm getting some like feedback here on the recording. Thank you. Awesome. Okay, so let's go ahead and balance the reaction. So we need a 2 here, and we need a 2 there. Okay, and so that is a synthesis reaction. Why don't I have a quick like mute all button? Manage participants, mute all. Yes. Okay, there we go. That's easier. All right. I wish I had that button in school. Just like, boop, everybody's quiet. All right, you know, this is also a redox reaction. So let's go ahead and like do a little redox review here on this. Let's assign some oxidation numbers. Elements in their standard states are 0. And then of course, in this ionic compound, they've got charges, a +2 and a -2. That's a real simple, easy little redox. You can see that the magnesium is going from a 0 to a +2. How does it go from a 0 to a +2? Loss of electrons, which is oxidation. And the oxygen is going from a 0 to a -2. So the oxygen is gaining the electrons, and that is reduction. So yes, this is a synthesis reaction, but it is also a redox reaction. There's an exchange of electrons going on there. So you've been doing redox reactions all along and just not sort of recognizing them as such. Okay, so let's move on to a decomposition reaction. Everybody's favorite decomposition reaction is the decomposition of hydrogen peroxide, which when you use the 30% hydrogen peroxide is elephant's toothpaste. It's the demo that you guys did for the parents on open house. Seems like ages ago. And if we want to decompose this, of course it's aqueous if we're talking about 30% solution, meaning it's dissolved in water. This decomposition does happen naturally, and that's why hydrogen peroxide is in those dark colored bottles, is to prevent it from decomposing into water and oxygen. That's why hydrogen peroxide is kind of a nice thing to use as a disinfectant, because once you've wiped something down with hydrogen peroxide, after, you know, a couple minutes, it's totally safe to be on that surface because it decomposes into water and oxygen. As opposed to like if you were to bleach your whole house, you know, somebody in your family is sick, Sophie's catching a cold, you know, Sophie's gonna go and she's gonna like wipe down her whole house with bleach. That bleach remains, it doesn't decompose. So if you're gonna bleach something, you always wanna wipe it down with water if you're gonna eat off of that surface. But hydrogen peroxide is nice because after time, it just decomposes, and so it's totally safe on your surfaces. Okay, but anyway, that decomposition happens in the presence of UV light. So we keep our hydrogen peroxide in dark colored bottles. And if we want this reaction to happen faster and be more exciting, we need to add a catalyst. And if we're going to have catalysts in our reactions, we write them over the arrow right here. So we would put, you could use manganese, just, you know, pure manganese metal. You could use potassium iodide. Whatever your catalyst is, you're going to put it over the arrow. And then, of course, we need to balance this. So that's a decomposition reaction when you've got one reactant. So you'll know it's decomp. Oh, I kind of ran out of room here. If there's one reactant. Okay. Let's move on to single replacement. So a single replacement reaction, you know that you're going to have one free element and an ionic compound. So it'll be a free element plus an ionic compound. So let's say I have some aluminum solid and some copper chloride solution. You want to look and see what is this free element. Is this free element a metal or a non-metal? Because you can have single replacement reactions that are cation replacement, where the metal is replacing the metal, but you can also have anionic replacement, where the free element is a non-metal, in which case it would be trying to replace the non-metal in the ionic compound. So this is a cationic replacement, and you would want to check to see if aluminum is higher than copper on the activity series. But some of you are probably like, wait a second, I know that this is a redox reaction. And really what I'm checking is my reductions potentials list. We'll get into that in a second. So let's imagine that we're back in Honors Chem, we check our activity series, and yes, aluminum is higher than copper on the activity series. So copper is going to get kicked out, and I'm going to see a copper solid precipitate. And the solution is now going to be an aluminum chloride solution. So you got to balance your charges there and think about your solubility rules, and that's soluble. So my solution is originally going to be blue in color because copper ions in solution are blue. But as those copper ions precipitate out as copper solid atoms, that solution is going to become less blue in color. So sometimes you're going to have some sort of descriptive chemistry on either on the AP exam or on the subject test. All right, so let's go ahead and balance this. This needs to be a 3 to get to 6 chlorines. This needs to be a 2, 3, and a 2. Okay, so back to like the activity series and like what's really going on here, let's assign our oxidation numbers and see if we can see what's going on in terms of the redox. So here aluminum is a 0, and over here aluminum is a +3. So the aluminum is being oxidized, right? So the aluminum going to the aluminum 3+ is doing that through the loss of 3 electrons. And the copper, which is going from a +2 here to a 0 there, the copper is being reduced. The copper is gaining 2 electrons. Now, of course, I didn't balance my electrons here. I probably should have done that. Copper with no charge. So, of course, this one's being multiplied through by 2, and this one's being multiplied through by 3. So really the transfer of electrons is 6 moles of electrons being transferred. But anyway, because the aluminum is being oxidized and the copper is being reduced, that must mean that the copper is higher on the reductions potential list than aluminum, which is why aluminum is higher on the activity series than copper. Like the reduction potentials list is like an upside down activity series. I don't think that that's something that you actually like need to know for the exam, but I think it's interesting, right? So like the activity series that you were using back in like baby chemistry is based off of reduction potentials, like who wants the electrons the most between these metals. And the copper ions want electrons more than the aluminum atoms do. And so that's why that transfer of electrons can take place, is really because of their reduction potentials. Isn't that interesting, everybody? I know. I'm imagining you nodding and smiling your faces at how fascinating that is. Let's do a double replacement. Let's do, what color was I using? Blue. Okay, double replacement reaction. Let's do, let's do sodium carbonate, Na2CO3 solution, plus calcium nitrate solution. Okay, remember, double replacement is just where the partners switch. So the metal sodium is now going to be with the nitrate, and the metal calcium is now going to be with the carbonate. And this is where your solubility rules come into play. Oh, you guys, Austin, remind me at the end of this to talk about that amazing document that you made. Because, okay, yeah. So solubility rules reminded me of that document. So we'll talk about that at the end. Okay, so switch your partners. NaNO3, alkali metals and nitrates are always soluble. So that's going to be aqueous. And then my calcium is going to be with my carbonate. And that is going to be a solid. If it wasn't, like if my two products were both aqueous, nothing would have occurred. Like there would have been no reaction. So double replacement reactions are often characterized by the presence of a precipitate in the product. Okay, so you're usually going to get a precipitate. Sometimes you'll get the formation of like liquid water, or you'll get the formation of a gas. If you don't get one of those three things on the back side, then if everything's aqueous, if you were to do a net ionic equation, everything would cancel out and it would look like nothing was taking place at all. So make sure that when you look at these double replacements that you're on the lookout for that precipitate or that liquid or that gas. So let's balance this. We need a 2 there. Oh, I guess that's it. That's an easy balance. Okay, so if I was doing a net ionic, you guys, see how the sodiums are aqueous at the beginning and aqueous at the end? So they're spectators. These are Elise's favorite. She gets so sad canceling out the spectators. It's going to be okay, Elise. All right, so the sodiums, bye-bye, they don't matter. Okay, now the carbonates, they start off aqueous, but then they precipitate out as a solid. So we're not going to ever want to, somebody's printing something, that's very loud. Okay, so, and distracting. So we're not going to cancel out the carbonates. Okay, so my carbonates, if I'm doing a net ionic equation, you guys, my CO3 2-, these aqueous ions, those are a player in the reaction. And so are the calciums. So the calcium 2+ ions, they're not going to cancel out either. So I'm just going straight to a net ionic here. And my nitrates, those are spectators. My sodiums, those are spectators because they would cancel out with the sodium and the nitrate over here. But really all that's happening in this reaction is, oh my God, Savannah must be printing out her whole week's worth of work. The carbonates are bonding up with the calcium ions in solution and precipitating out as calcium carbonate solid. I think being able to write a net ionic equation is important in terms of being able to visualize like what's really going on at the microscopic level. So like if you had to, you know, draw one of those particle level diagrams where you have to show the things floating around in solution and show what precipitates out, that's when it's helpful to look at your net ionic equation. Okay, so let's add, those are 4 of our main types, well, combustion being the 5th, but I decided to add in right here after double replacement, acid-base neutralization, because that is a type of double replacement. So let's say we were doing an acid-base neutralization between HF, hydrofluoric acid, aqueous, and NaOH, which is our base. This is a double replacement reaction, right? So you just switch your partners. And so you're going to get a salt, NaF. That's going to be a soluble salt because of my alkali metal. And HOH, otherwise known as H2O. So here's your double replacement reaction where liquid water is one of your products, right? That's what I was talking about up here. And of course, this is all a one-to-one-to-one balancing. So acid-base neutralization is very simple. Oftentimes, they just make acid plus base, make salt and water. So it's just a type of double replacement. Now, it's not always a one-to-one-to-one mole ratio, right? If you have a diprotic acid or a triprotic acid, you could end up with some different mole ratios in here. And there's another type of acid-base neutralization that I want you guys to pay attention to. And that is when, let's see, let's do HF with sodium bicarbonate. Okay, so this is my acid. Now, this is actually a base. This is baking soda. And so this is, oh, Ellie. Hi, Ellie. This is another type of acid-base neutralization. So let's do our double replacement, right? So let's switch the partners, the hydrogen that's in the front here and the sodium there. So we're gonna get that same salt. We're gonna get some NaF again. And the other product is gonna be H2CO3. And you're like, wait a second, isn't that carbonic acid? Like, doesn't this look like we just produced an acid in that neutralization reaction? Yes, but carbonic acid, if you have any reaction, you guys, that produces carbonic acid, you should just sort of automatically know by this point that carbonic acid at room temperature and atmospheric pressure automatically decomposes into liquid water and carbon dioxide. It's a very, very weak acid, and it automatically at room temperature decomposes. So this is a acid-base neutralization reaction that results in the production of a gas. So like that can happen as well. And so that's like why when you neutralize vinegar with baking soda, or you do that little baking soda volcano thing, that's why you get those bubbles, is because of the decomposition of the carbonic acid that you're producing. I think that's all I wanted to talk about in terms of acid-base neutralization. I'm just checking my review book here. Yeah, that's all I wanted to talk about. Okay, everybody good? Chat screen is awful quiet. Hopefully nobody's snoozing. It's just that this is so easy, right, you guys? All right, let's do combustion. Technically, combustion is a reaction of anything with oxygen. So any reaction with O2. I know that's a little weird, right? But like rusting, you know, like when the iron on your car rusts, when it oxidizes to make rust. F. My handwriting was so good last night when I recorded the video, and now it's like trash. Maybe I just need to slow down. This, you guys, this reaction right here is technically is combustion. Are we printing out our entire week's worth of work there, daughter? Can you tell what a good mood she's in, everybody? I know, it makes me want some. Okay, did I balance this correctly? I have 3 here. This is combustion. Okay, so it's like boring combustion or whatever. It's not very exciting. The more exciting type of combustion that you guys are used to working with is burning stuff. So like if we have methane gas and we burn that in the presence of oxygen, we always, always, always get CO2 and H2O. Oh, now the chat's going. Does O2 have to be a reactant, or can O2 also be a product in combustion? It's always a reactant. Yeah, oxygen's always a reactant. Now, it's going to obviously be present in whatever compounds form as the product. Why does iron have a 3+ charge there? That's just the charge that iron has in rust. There is iron oxide that is FeO with a 2+. Like, this is also a thing, but I was showing the formation of rust, and rust is iron 3+. So nature does what nature do. And then you might be wondering, well, like, how is it that I get this type of iron oxide compound versus that type of iron oxide compound? It would have to do with the conditions under which that compound was being formed, you know, the temperature and pressure conditions. Yeah, so is that good? Did I answer your questions, Austin and Theo? Hope so. So that's not rust. This one is rust. Okay, so these products are going to be gaseous because these reactions are really exothermic. And if I was balancing this, balance your carbons first, 1 and 1, then your hydrogens is an easy one, 2, 4, 4 oxygens. So that's a super easy balance. Sometimes the combustion balancing can get a little funky because of the oxygen both in the water and in the carbon dioxide. Very slouchy this morning. Okay, so what else did I want to talk about? Oh, I know. Another sort of nuance about combustion is that when we say something undergoes complete or totally clean combustion, we get nothing but carbon dioxide and water. In incomplete combustion, you also get a little bit of carbon monoxide produced. So you'll see some combustion reactions that also produce carbon monoxide, like when we're burning gasoline in our car, we do get CO2 production, but we also get some carbon monoxide production, which is why you're never going to warm your cars up in the garage. Carbon monoxide being toxic. Okay, so that's it for combustion. And we already talked redox, you guys. So redox reaction is when there is a transfer of electrons. And you just look at your oxidation numbers to see if there was a change. And if there was a change in oxidation numbers, that reaction was also redox. So like, for example, this rusting of iron was redox. So this was a 0, this was a 0. And then you guys nicely asked the question about why is iron a 3+ here. Well, in this particular redox reaction, that we get 6 moles of electrons being transferred, and the iron goes from a 0 to a +3, and the oxygen goes from a 0 to a -2. So we can see here that this is my loss of electrons. So my iron is being oxidized, and the oxygen is going from a 0 to a -2. It's gaining electrons, so it is being reduced. And if I looked at the balance there, the total magnitude of charge balancing, 6 moles of electrons are being transferred in that reaction. So I'm not going to redo a redox reaction because I think you guys got it. Like, we've been doing a bunch of redox reactions. See above. Okay. And net ionic equations. We did a net ionic equation. We did one of those above too. I just jammed it all into one thing, right? Here's a net ionic equation. Does anybody want me to do a fresh net ionic equation? Probably not. Right? Rules for net ionic equations: separate anything that's aqueous and then cancel out spectators. Maybe we'll just write that down. So net ionic equations, you're going to separate all aqueous species. And then you don't separate solids, liquids, or gases. And then you cancel out the spectators. Boom. Easy, easy. Any questions on reaction types? I'll kind of pause there for questions. And then we'll talk reaction energy diagrams, and then we'll be done. Can I scroll up a little? Yes, I can scroll up. How far are we scrolling? Farther? Got it. Awesome. Okay, so let's talk about energy involved in reactions, shall we? Here we go. Maybe I will give you guys a chance to, I'll go ahead and pause the recording here for a second and give you guys a chance to diagram those. Okay, so these reaction energy diagrams, you guys, are just diagrams showing how much potential energy do the reactants have versus how much potential energy the products have. Okay, so potential energy here is on your y-axis, and reaction progress on your x is like time. So here in diagram A, we can see that our reactants start off, you know, pretty low energy. And then there's this sort of like energy barrier in play here. Like the reactants need to gain energy in order for that reaction to occur. And really what's happening, you guys, is like a collision. Like in order for bonds to be broken and formed, for new substances to form, there has to be a collision between those particles. And so what you're looking at up here at the top is where that collision is occurring, where the collision occurs and the bonds break and reform to make new substances. And so the amount of energy needed to go from the reactants up to that peak, oops, come on, pen. Try the blue. This distance, reactants, oh, I don't understand why I can't draw a straight line. Maybe I should go faster. There we go. Reactants to peak, that's our what we call our activation energy. And that's where the collision is occurring. It's this top of our peak right here is called our transition state. And the energy required to get up there is your activation energy. And then when the bonds, you know, break and reform and we have products, those products have a certain amount of potential energy. If your products end up with more energy than your reactants, this reaction absorbed energy. That's a positive delta H, and this is showing us an endothermic reaction. Again here, looking at this diagram B, however much energy the reactants need to get up over that transition state, reactants to peak, this is your activation energy. And then the delta between where your products end up. So in this case, our products end up more stable than our reactants. They have a lower potential energy state than our reactants. This would be a negative delta H because it's always products minus reactants. This is a negative delta H, and this is an example of an exothermic reaction. Any questions on potential energy diagrams? Okay. And is now a good time to talk about all the different ways to measure delta H of a reaction? Maybe it is. Delta H of a reaction. Like, how do we actually measure this thing that's being shown here on this diagram? 3 different ways. One way is in the lab. Q equals MC delta T, where we actually measure the temperature change of a reaction. We multiply that times the specific heat and the mass of thing that's changing temperature, and we get a Q. Now, remember, the Q is typically measuring the Q of the surroundings. Like usually this reaction is happening in water and we're measuring the temperature of the water. And so that's the surroundings. The Q of the surroundings is always equal and opposite to the Q of the system, being typically the reaction. So the Q of the system is also called the Q of the reaction. So these 2 things are the same. So if the reaction is, or if the surroundings are getting hotter, like if this is a, if we end up with a positive delta T and a positive Q here, that means that the reaction was exothermic. the reaction was releasing heat. Versus if we ended up with a negative sign of our surroundings, the surroundings were losing heat, they must have been giving their heat to the system, to the reaction, and the reaction would be endothermic. So, you know, your signs there can switch, but they're always just equal and opposite. I don't like how I wrote that. That looks very confusing. Too many things. Let's just call the system the reaction. That looks better. And then if we want to turn this magnitude of heat into a delta H, you would have to then divide this by the moles of your limiting reactant. Because when we write this as a delta H for a reaction, it's always per mole of your balanced chemical equation. And if we reacted a whole bunch of it, we're going to get a huge Q value. And if we only reacted a little bit of it, we're going to get a very small Q value. So to get this into a standard value, to get this into a delta H, you divide by the moles of your limiting reactant. So that's one way to get a heat of a reaction. Another way is everybody's favorite, where we take the sum of the heats of formation of the products, and we subtract from that the sum of the heats of formation of the reactants. That's another way. We can also use Hess's law, where we take a bunch of reactions and sum them up in order to get the delta H of the overall reaction. And then lastly, we can get the delta H of a reaction by doing the bond enthalpies. D is for bond enthalpy of the reactant bonds. So it's like bonds that are broken minus the bond enthalpies. I don't know why I'm trying to like squish everything over here. Minus the bond enthalpies of the product bonds. That's the only one that's switched, right? So it's like another way to remember this is bonds that are broken minus the bond enthalpies of the bonds that are formed. And bond enthalpies are always positive values. Like that's how much energy do you need to put in to break apart the reactant bonds versus how much energy you would need to put in to break apart the product bonds. Okay, so those are always, bond enthalpies are always positive values. Oops, I just made a random weird line. Okay, but everything else is always products minus reactants or final minus initial. So when you're talking about heat needed to form those substances, that's a different amount of heat than the heat that you would need to break apart those substances. Okay, so these are kind of opposite things, heats of formation and bond enthalpies. That's why they're reversed from one another. Okay, so that's where we get all those delta H values. That was sort of a thermo side note. Okay, last thing for today, you guys, we'll be looking at a multi-step mechanism. Okay, so here, this is another just potential energy diagram. But this potential energy diagram has two activation energies, which must mean that this reaction is going through two steps. And this is gonna be a nice intro into our Unit 5 review later in the week, where we talk about reaction rates. So if I'm looking at the distance, so here are the reactants. So this RH plus X, these are my reactants, obviously. And this final stuff here, the Rx plus X, these are my products. So that's easy. Those two are easy. And the amount of energy needed to get these reactants up over to this first peak, this is my activation energy for the first step in the reaction. Okay, so like this right here would be your activation energy, you know, number one, if you will. And up here, what you have is, you know, a transition state. The things that get formed after that first step in the reaction, these are called your intermediates. Remember, these are the things that get produced and then immediately consumed in the next step. So this R plus your X2, these are your intermediates. And then the amount of energy needed to get, they didn't they didn't actually list this as one of the things on the side, but who cares? We're labeling this on our own here. This amount of energy needed to get the intermediates up to their transition state. This would be like your activation energy for step number 2, right? So this would be step 1's activation energy. This would be step 2's activation energy. And this is another transition state. And then we've got our products. This amount of energy between how much energy the reactants have versus how much energy your products have, of course, is your delta H. And this is going to be negative. This is an exothermic potential energy diagram, even though it's a multi-step mechanism. So the only difference here is that you've got, 2 transition states, you've got 2 activation energies. And from this, you guys can identify what the slow step in the reaction is. And the slow step is step 1. So in this reaction, step 1 or reaction number 1 is what we call the rate limiting step. This is our slow step. Now the slow step is not always the first step, but in this case it is, because the activation energy for that first step is much greater than the activation energy for the second step. So if we look at the way that they've labeled these things, like they say that they're calling this first transition state the rate limiting transition state, right? Because you're only as fast as your slowest reaction. Okay, and then this would be the non-limiting transition state. But I don't expect you guys to be able to, use that particular vocabulary, but I would expect you to be able to look and see whoever has the higher activation energy is going to be your slower step, and thus your rate limiting step. And that's the step that we're going to write our rate laws off of, but that's not until our next review. Okay, so I'm going to stop recording. Let you guys ask some questions, and then I'll talk about the stoic practice problems.